Hello everyone and welcome to Blackboard Biology. Now today we're actually doing some physical science, and maybe one of these days I'll get around to maybe changing the name to Blackboard Science or something like that, but today we're going to look at physical science. Specifically, we're going to look at a very curious field of science that has to do with energy and particles and force fields and charges and things known as electricity. We're going to look at electric charges and forces today. These are very strange things. So many strange phenomena that occur within this field of electricity. And so today we're going to just very kind of dip our toes in the water in the basics of electric charges and forces. So let's just dive right in. Well, the first thing we want to discuss is electric charges. What are charges? Well, charge is kind of this property of matter. And so when we talk about charges, we are talking about something that is there with particles. Now there's a great debate that goes on around physics, and especially in the world of particle physics, about whether the universe, whether everything we see is composed of particles, whether it's composed of force fields instead of particles, or maybe it's a mixture of both, that there's particles and these particles have force fields. We're not going to get into all of that today, but we are going to look at particles and force fields. They will both come into play with this. And so all matter is composed of atoms, right? And within these atoms, or not really within, they're composed of, these atoms are composed of more basic, more fundamental particles, protons, neutrons, and electrons. Well, protons possess a kind of property that is positive charge. We consider it positive electric charge. And so in this kind of drawing that I have here, we're going to label this a proton. It has positive electric charge, which would make this other one, the blue one, an electron that has negative electric charge. And of course, as we said a moment ago, neutrons, well, they're neutral. They have no charge. And so what we find here is that there are lots of misconceptions surrounding the terms electricity, electric charge, electric current, voltage, all of these things. And so I hope to clear up a few of these misconceptions. So here's a proton and an electron. They each have electric charge. The proton has positive charge, the electron has negative charge. And so what we would find is that all kinds of things actually possess certain amounts of electric charge. So when we talk about quote unquote charging things up, it's not necessarily that we are giving it more electric charge so much as it is that quote unquote when we say charge something up, what we really mean is we're creating an electric potential difference, or maybe we're giving it more electric energy, which is different than charge. And so normally what we find in most objects is that most objects are actually, they tend to be neutral, because the amount of charge on a proton, the amount of positive charge on a proton, okay, so we'll say positive charge on a proton is actually equal to the negative charge on an electron. So that they basically, quote unquote, kind of cancel out. They zero out. They kind of neutralize each other. And so what we do with this information is that we look and we say, okay, objects tend to actually be neutral, but we get these electrical phenomena that occur when we separate these charges from one another that are there, that are normally kind of canceling out. We can create these electrical phenomena. And you're familiar with these. You've probably had some kind of scenario where you've walked across maybe a carpet in your socks, or perhaps you've taken laundry out of the dryer and socks are clinging to towels or something. Well, what has happened is that there's been a transfer of charge. Okay, so let's just kind of clear some things here and let's take a look at this. And so what would normally happen would be if we had a sock here. Let me kind of draw a little loose interpretation of a sock. Okay, so we have this sock here, and within this sock, there's all kinds of particles, right? It's made up of atoms, and those atoms have protons and electrons, and normally this sock would be neutral. Under the most normal of circumstances, this sock right here would be neutral. But what's going to occur is that we are going to, if it walks across the carpet, all of these positive charges and all of these negative charges, it's a little thick there. There we go. All these negative charges, okay, they should be, you know, roughly equal. What happens though is that when you walk across the carpet actually will give away some of its negative charges. And so let me, let's go with green carpet here. Why not? So we've got some green carpet here. And again, the carpet has these positive charges, just like the sock does. And it also has negative charges, just like the sock does. But what happens is when you rub the socks across the carpet, because of the properties of the two materials, the sock will actually gain electrons. Often it will gain some of these negative charges, and so they will actually move to the sock and kind of cling to it. So the negative charges are going to move to the sock. Well, what we have created here by this is we have this excessive buildup of negative charges in the socks. And they've moved from down here, and so what we've done, because all these negative charges, and there would still be some, okay, there'd still be a few down here, but we've created an overall charge difference. We have separated, or we could even say pressurized, the charges, so that up here we have a largely negative region on the sock, and down here we have a largely positive region at the carpet. And so what happens is you have this difference, this buildup, this separation of positive and negative charges. And what happens with charges is that opposite charges, positive and negative charges, like each other, they will be attracted. So that if you have built up this separation of charges by rubbing your socks across the carpet, if you go touch a doorknob or something else that is a good conductor, you will get a shock, right? And we call this phenomenon static electricity. Static is misleading, though. It's not that nothing is flowing. It's not that things are not moving. It's where you've built up excess electric charge. You've had a separation of the negative and the positive charges that normally are together and kind of neutralizing each other. And so nature wants to correct this imbalance. And so what will happen when you touch an object is these charges will flow and they'll try to balance back out. And you get this sensation of a shock when that occurs. Now, the reason this can happen is this lovely thing called the conservation of charge. Or we could even say the law of conservation of charge. And so what occurs with this is that charges, much like how we would talk about the conservation of mass or energy when we're talking about chemistry, these charges can be transferred between objects, they can flow, they can move, but charges cannot be created or destroyed. And so the total charge overall in this scenario doesn't change. They simply move. And so I hope this begins to clear up some misconceptions that we may have about this. And so we have like charges. Okay, if we have two positive charges, well, they would actually do the opposite of this. They would repel. Okay, you've probably played with magnets. Magnetism is it's very connected to electricity. In fact, they call it electromagnetism, but anyways, sometimes. So the electricity and magnetism are highly related and they behave in some similar ways. So if you have like charges, they repel. So two negative charges, they repel. Two positive charges, they repel. But if you have opposite charges, a positive and a negative, they are attracted to each other. And in fact, that attraction is quite strong. The attraction, the electric charges, the attraction that they have is actually greater even than gravity. When we talk about at the particle level, the attraction between protons and electrons is actually so much stronger than gravitational forces. And so what we talk about, these charges, the way that they behave, we say they exert force. They exert push or pull on each other. Well, how do they do this? How can particles exert push or pull on one another? How are there forces at play here? Well, we can think of these charges, these particles, we can think of protons and electrons, and in fact some physicists do. They think of them not merely as particles, but as force fields. Okay, and so these right here, we're going to show basically electric force fields. So whether you're thinking about the proton as a particle or as a field, or you're thinking of the electron as a particle or as a field, that's not necessarily relevant right here. We just want to talk about the actual field for a moment, the force field around it. And so what happens is these charges exist within what's called an electrical field, an electric force field. And so they exert forces on one another. And every charge is again, it's surrounded by an electric field, and that can exert forces on one another at a distance. The particles don't actually have to be touching. Again, you've experienced this with magnets, where you put a magnet, suppose you put two of the positive ends of magnets together, and they repel, but they don't actually ever touch. They work at a distance because of the magnetic field. Well, an electrical field works the same way, so that these particles can interact at a distance. And they're often represented by diagrams, much as like the one that I have here. So this positive charge, the way that diagrams are typically shown by convention, meaning everybody just kind of decided to do the same thing, by convention they said, hey, let's represent an electric field diagram for a particle based on how it would interact with a positive charge. So here we have a positive charge on the left side, okay? This is positive on this side, and you see that the arrows actually point out away from it, and they say that basically what they're meaning is if you put another positive charge, okay, so if I brought another positive charge in here, it would be repelled. It would be actually pushed away from this positive charge here because of its electric field. As the lines get closer together, notice they get closer together the closer you get to the actual, again, you could say particle here. As you actually get closer, the lines get closer together. Whereas out here, they're further apart. Well, in these diagrams, the further apart the lines are, the weaker the force. As the closer the lines get, the stronger the force. And so what we find is that the forces, electric forces due to force fields of these charges is affected by distance and again by the actual charge, by the nature of the particle itself. And so again, over here, if we had on the right side, if we had a positive particle, it would be attracted here, whereas over here it's getting repelled away. And so that is kind of how these force fields work. And what we find is that there are some materials, again, everything has electric charge, because again, charge is a property of those particles. It's something that protons have, it's something that electrons have. Well, everything has protons and electrons, and so everything has electric charge. It is when we can get these charges to flow, or just simply to vibrate, or we can separate them, that we get these phenomena that occur. And so what we'll find is that some materials are, their charges more readily flow than others. And so we call those materials conductors. Okay, so a conductor is a material through which electric charge flows easily. Okay, so it's a flow of charge. So in other words, it conducts, it can carry an electric current very easily. On the other hand, some materials are what we would call insulators. Well, they're going to do the opposite. They actually don't allow charge to flow very easily. Electric charge does not flow easily. Okay, so examples of conductors, obviously you have some experience with this. Metals. Metals are very good conductors. Okay, if you walk across a carpeted floor in your sock feet, you are going to build up those electric charges, excess electric charges on yourself, especially your socks. And then if you go touch a doorknob and you reach for that metal doorknob, then those negative charges can flow very easily from your hand to the doorknob because it is a good conductor. It's a material through which electric charge can flow easily. Insulators, on the other hand, if you touch them when you have this buildup of charge, you may not get the same shock. It's just not going to work very well. An insulator could be something like glass. Glass is a good insulator. Because of the properties of the glass, because of the particles that make it up, the way they're arranged, glass does not allow electric charge to flow easily through it. Plastic coating around electric wires. So if you've ever plugged in an electrical device, if you've ever plugged in, I guarantee you're watching this on a smartphone or a tablet or a computer. Those all have, we call them power cords, right? The charging cords. Those cords are surrounded with plastic because inside of them they likely have copper wire. Copper is a good conductor. The electric charge flows easily through it, and so because of that charge flow, it's able to carry electrical energy along. And because the electrical energy flows along around the outside of that wire, we need something that coats the outside of the wire to protect us from that flow of charges that carries energy. And so we need to protect ourselves from that with an insulator. Plastic, we surround those things with plastic wrapped around it. It's not a good conductor, it's an insulator. And so that protects us from those things. And so there's different ways that we can create this difference of charges. There's different ways that we can build up charges. We can do it by contact. For example, again, the rubbing our feet across the carpet. Okay, we can do that. We can create this charge difference, this electric potential difference. We can charge by contact, touching things. Okay. So some examples of charging by contact would be socks on carpet. Whoop. Another example would be, rubbing a balloon, right? If you rub a balloon on things, you actually cause it to gain electric charges. And so, socks on a carpet, rubbing a balloon. Okay, and these can create charge differences by contact. Well, on the other hand, we actually have a different thing that can occur where we can charge by what's called induction. All right, and charging by induction is a bit differently. What happens with this is we have an already charged object that gets near a neutral object and causes a rearranging of its charges. A rearrangement, typically it's the electrons rearranging. So a good example of this, of charging by induction, is kind of like when you have a storm cloud and it's about to release lightning. When you get this phenomenon of lightning occurring here, what happens is we get a cloud that's negative at the bottom. Can't really spell, let's see here. The cloud is negative at the bottom. And repels negative charges on the ground. And so what happens is, because it's negative at the bottom and it repels negative charges on the ground, you get this build up of different charges. And what do we know about different charges? Well, they're attracted to each other. So let's kind of explore this for just a moment and then we'll wrap up the video. Let's explore this kind of charge by induction. So imagine with me that we have a lovely storm cloud up here that's just, it's brimming with charges. Okay, and this phenomenon is not entirely 100% understood, the processes by which this occur, but we do know that the water droplets, some of the water droplets lose electrons and other ones gain electrons, and so some of them become negatively charged. Well, these negative charges tend to gather at the bottom of the cloud. So through just various events throughout the storm, the negative charges actually separate from the positive charges. And again, that separation of positive and negative charges is what we refer to as static electricity. Again, static is misleading. This is all about to flow. Things are about to move here, but it's when we separate the positive and negative charges that we call it static. So we could really call it maybe pressurized electricity instead. That might be a better term. And so because of all this flowing and churning and things within the storm cloud, we just end up with negative charges at the bottom and positive charges at the top. Well, down here we have the ground. Nice green area. And I don't know, maybe there's a house here. Lovely house, right? I know you're all dying to live in that kind of house. And perhaps over here we have a, looking for a decent, I don't really have any good colors over here in my color palette for a tree, so we're gonna go with something a little funky here. So let's say we have this tree over here. All right, there's our lovely tree. All right, and so what happens is during this event, this is such a strong separation, such a strong buildup of negative charges that they actually repel all the negative charges on the ground. They repel them away. And so you get in this area this buildup of positive charges in the ground and the objects around. So we've got all these positive charges just hanging out, all kind of separated, and nature likes balance. It wants things zeroed out, things kind of canceled. So we get this buildup of negative charges up here in the cloud. We get this buildup of positive charges right here, and it just needs a pathway. It just needs a way to get to the ground. And so what it does, it releases this. These finally break through. There's enough attraction between them to overcome the distance. And you get this just big flash of lightning, and it goes through and it's going to hit the ground. Now, if somebody was in that area as this occurred, as the negative charges were being repelled from the ground in the air, they may experience a tingling sensation as some of their negative charges were being repelled. that would not be a good thing, okay? They would want to get out of there and get to a safe place, because that lightning is going to seek a pathway, okay? It's this massive release of these negative charges that are going to flow, and it needs a pathway. When it does this flow, this electric current, this flow of charges is capable, it basically acts as a medium through which lots and lots of energy can flow. And so it can carry along, kind of like how sound waves work. The air particles themselves are not traveling around at 720 miles per hour. It's a wave. The wave travels through the air particles. They act as a medium that carries the wave at such a high speed. Same with this. The charges themselves are not rapidly necessarily always moving that fast. The charges are acting as a medium that carries the energy along like a wave. And so this is very dangerous, because this is a massive amount of energy. It momentarily heats the air surrounding this event several times hotter than the surface of the sun. And so you get this rapid expansion of these gases as they're heated, and that's the thunder. This rapid expansion of gases, it disturbs the other air, they bump and disturb all the other air particles around them, and it carries that disturbance as a wave, as a sound wave, and we hear thunder. So what do? How do we avoid things like this? Well, we allow for grounding. Grounding is where you take something and you build a pathway, basically. You provide a path for the charge to reach Earth and prevent this charge from building up in the first place in such a manner. And so on really tall buildings, for example, if you were to go to many large cities in the world, and the very tall buildings, let's pretend this is a skyscraper here, it might have a big lightning rod on the top. And it's going to be metal, and it will safely be grounded all the way down. It will literally run down into the earth. And so it will have some kind of pathway that safely carries it. It's probably insulated around it. Some kind of pathway that safely carries it down to the ground, so that this massive buildup of charges can somewhat be avoided. And even if it happens, it will be attracted to the metal because it's a good conductor, and safely carry it through a path to the ground that would keep it from flowing through humans, or flowing through electronic devices, or flowing through other parts of the building that would be damaged by that amount of energy. And so this has kind of been a good little introduction to electric charges and electric force fields. In a later video, we'll actually get into the concept of electric current, where these charges flow and they move. Or in the case of alternating current, they don't even actually largely move around so much as they just vibrate basically back and forth, kind of like air particles do when they carry sound waves. And so I hope that this video has been helpful for you and kind of hopefully cleared up a few misconceptions. As always, I want to encourage you to like the video, subscribe to my channel, leave me comments if you have questions, and request future videos. And as always, thanks for watching.